Here we are, good morning. It's the physics video lecture, Physics 2A video lecture 17. We're moving on into a new chapter, but I'm going to review a bit on energy chapter 5 anyway. And in particular, I want to set up homework problem number 69. Homework chapter 5, problem 69. And then we'll move on. I'll do some demonstrations and so forth. Okay, so chapter 5, problem 69. For the energy conservation aspect. So this is an Atwood machine, so-called, and it's possible to analyze it completely with Newton's laws, tensions, forces, etc. And here's what we have. We have that tabletop, and there's a mass here. It's connected to a second mass over a big pulley. Okay, so there's a pulley, an axle. Pulley's hooked up to the ceiling somehow. Okay, so it's connected via a pulley, and I think we're calling this M1 and this M2. The idea is we're going to let go of M1, and it's going to drop down, and M2 is going to go up, and it's got a string connecting them. In fact, I need a little more room on my drawings. I'm going to start up a little bit higher. Okay. And we know that M1 is greater than M2. I don't intend to plug any numbers in. It's sufficient to know that M1 is greater than M2, and that we have this initial height off the tabletop. So the tabletop is our natural y equals 0. Okay. So we're going to solve this problem using energy. Like I said, we could just use Newton's law, and we'd use Newton's law on both of these. That's a great exercise in itself. But just using energy is interesting as well. What I'm going to do is label this as A, and then when it falls down and they pass each other halfway, we'll call that B. And C is when this one hits the tabletop and this one goes up, but I'll leave that for you guys to deal with. So this is B, and M1 and M2 when it's coming down, and this one's going up. Okay. Because I like to set these things up in the following way. E sub A is equal to E sub B. We're using energy. Okay. And it's going to be kinetic plus potential at A is kinetic plus potential at B. Now, kinetic at the initial, so kinetic plus potential at A equals kinetic plus potential at B. Okay. Now, kinetic energy at A is 0 because we're releasing them from rest. So we have a 0 there. Potential energy at A, we can say it's just M1GH. This is the only one that's elevated. M1 times G times H. So plus M1 times G times H. Now, kinetic energy at B, M1 is dropping down, M2 is going up. But they both, they're passing at the same height, and they both have the same speed because it's just a string pulling them. So what we have is 1/2 M1 V squared, right? They both have the same, I'll go ahead and call it A. We have 1/2 M2 V, that's got to be B, okay, sorry. M2 VB squared. So that's the kinetic at B, and what's the potential energy at B? They both have H over 2 as a height now. H divided by 2. So that's plus M1G H over 2 plus M2G H over 2. Should have left a little more room, but I'll outline this equation. we just wrote it down and the answer is actually just staring us in the face. Let's send this up. And once again, make sure, initially we just had the potential energy of M1. When they were both moving, they both had kinetic energy. They different masses, the same speed, because they're connected by a string, and the potential energies are M1G half the height, M2G half the height. So we just set that equation up, and I'm just going to write next, comma, solve for B sub B. And don't plug any numbers in, just solve for B sub B. Yeah. And this is part A of the problem. One more question. I'm not going to solve the whole thing. Yeah, good. So solve for B sub B. If you have an equation, you just have to make sure you don't make any mistakes. And I'll even get the ball rolling here. You're going to have M1GH, and then you're going to subtract these two off, minus M1GH over 2 minus M2GH over 2. Okay. Subtracted those off, equals 1/2 M1 plus M2 BB squared. And you see, it's going to progressively simplify. When you're done, you'll have a pretty simple formula, solve for B sub B. Okay. You can see you've got a half, H minus half of that. So, oh, I can't help myself. I have to work on this. So M1 minus M2 G H over 2, 1/2 M1 plus M2 BB squared. Okay, so I took it another step, and you see it's going to simplify the halves and so forth. So solve for B sub B. And now for the next half of the problem, next, we also have E sub A is equal to E sub C, right? E sub A is equal to E sub C. You set it up the same way. In fact, yeah, set it up the same way, solve for V sub C. And you're on your way. So that's purely done with energy. And you see the strength, the power of the technique that you just carefully analyze the system and write down a correct equation. Okay, so that's pretty good. And like I was saying, you could solve the whole thing with forces and tensions, and that would also be a good exercise, by the way. But here we wanted to make the point of how energy conservation is used. Okay, so enjoy this one. I'm going to move on to, you see I brought some demonstrations here. I'm going to move on to the new chapter. And good, we'll erase all this now. Okay, so chapter 6. Momentum and collisions. Momentum and collisions. And what I did was I brought some demonstrations in that I'll show right now, and we can refer back to them repeatedly, so I don't have to show them many times since they'll be filmed. But I want to demonstrate the collisions, which is what we're going to learn about in this particular chapter, as well as other things, and so I have some potential collisions here. I'm going to start, though, with the air track. And I have to wheel the camera so that we're looking at the air track. Get the whole thing in the frame. There we go, that'll work. So we had a demonstration of this before, and I'll just remind us of what we're looking at. So again, this is that track here, and it's a hollow channel and it has air coming out, and therefore these little cars or gliders float on it, and you can get nice frictionless motion. But I have more than one of them. I have a second one, and I just want to demonstrate the prototypical collision of a certain type. So these cars have Velcro on them, and so they'll stick together. And the other thing to note about these gliders is that they have equal mass. Okay, they're same size, equal mass, or very close to equal mass. This one's 200 grams, this one's 197. So for our purpose, they're equal. And there's a really typical collision when two objects collide and stick together. So you can see the speed with which one this approaches collides, and they glide off together much more slowly. Okay. What we'll calculate later is that for this collision, the final speed is exactly half of the initial speed. Okay. Exactly half. I'll send this one in again. Exactly half the speed. And this is referred to as a perfectly inelastic collision. That's the terminology when things collide and stick together. Now, I can also bounce them off their steel springs right here. And now we get another really typical phenomenon. So this one comes in at a certain speed. Dead stop, comes to a dead stop, and this other one comes back, it comes to a dead stop. This is only true with equal masses. Comes to a dead stop. So that's referred to as an elastic collision. Okay. Now, there's also something, let's see if this one gliding today. I've got this larger glider. I got to make sure it's not going to hang up. Sometimes I have a burr on them. Yeah, that one needs to go back to the shop. Let's see if this one. See if this one has a little smoother action. Indeed, it does. Okay. So I'm going to send a larger mass up against the smaller one. This is at least twice as massive. And what you'll see is it kicks that one out with extra speed. So this one does not come to a stop, and it also kicks that one so that it jumps out faster. Okay. So those are two really basic collisions. The one that we have the most control over is the equal masses, and then we see one comes to a dead stop, and the other one keeps going. Okay, so I've made my point on this, and I'm going to return to the track on the table. So we'll swing this around here. And let's see, that looks reasonable. Good. So this time I have a different frictionless track on the tabletop. And these cars, you know, they glide reasonably with reasonable lack of friction. And there's even a Velcro collision. The Velcro collision where they stick together works better on the air track. However, we have something else we can do. I can actually push one car with the other one, and they are not touching. So you probably are guessing there are magnets mounted in these cars and they repel, okay? They repel each other. But the interesting thing is these cars are going to collide and never touch, okay? I'm gonna send this one in. It will never touch that one, and yet the same, well, let's just do it. Send it in. There's the phenomenon. Dead stop. This one moved out with the same speed as that this one had, and yet they never touched. So that's kind of interesting. In fact, that's something we want to explain. Okay. So here it's a magnetic force. We know nothing about magnetic forces in our course yet. Over there it's an elastic force, and yet it doesn't matter what kind of force it is. Equal mass. As this, one comes to a dead stop, the other one shoots out. I can even add some mass to this one. Okay, so I've added a bunch of mass to this one. It's got another car on it plus the mass. It weighs 3 or 4 times as much now. And we're going to come in really slowly. And that one shoots out with greater speed. So the same phenomenon I showed you on the air track is holding true. Do this one more time. This one comes in slow. The little one gets kicked out with greater speed. So our goal is to eventually calculate what's going on here, okay? And it's gonna take a while to get there, but these will be the fundamental phenomena that I'm trying to explain. We can always refer back to these demos. And I have one more interesting and fun one. I'm going to remove this track. Okay, remove that track. And I brought a basketball, a tennis ball, and a little concrete block to drop them on. Okay. And we'll do a few of these. So you can see how they bounce. That's a collision after all too, okay? Now, I'm gonna put the tennis ball on top of the basketball. I'll do a few of these. You have to see how the camera catches this. Okay, tennis ball on top of the basketball. Not bad. Okay, let's do a couple repeats of that. Tennis ball on top of the basketball. Do 3 or 4 of these just to make sure we see it. And there, that one may have left the camera frame. Let's give another try. Tennis ball on top of the basketball. And once more. So you're seeing, and by the way, this is a fun thing to do. You try this yourself. Don't let it point at your face, because the tennis ball can actually get launched pretty with great speed. Here we go, once more. Okay, and once more. Can't resist. Very good. So what that is a version of the big car hitting the small car. Okay, the basketball kind of bounces as the tennis ball is still coming down, so it's a collision. The basketball is larger, the tennis ball gets launched. So I was just doing it from a couple feet. If you do this off the ground on concrete, you can get that tennis ball to go 20 feet maybe. Okay, good. So those were momentum and collision. First of all, I'm just going to write for your notes. Demos, demonstrations. We had inelastic collisions, and there we say objects collide and stick together. Objects collide and stick together. And had elastic collisions. And for the elastic collisions, we had the equal masses. And the phenomenon, I'll just call it exchange of velocities. Okay, that's right. Exchange, what's more we're feeling? Exchange of, it's actually not technically true. I'm just going to write exchange of momentum. Even though I haven't defined momentum yet, because I'm just referring to these demonstrations in lecture number 17. So you have your notes and you can always look at those demos again. Okay, so what we have to do is set up the formal apparatus with the concepts that we have in order to understand what we just saw. Okay, these are actually fundamental processes. And let's see. So let's check our time here. Good. What I have to do is introduce some new concepts. And we're going to begin with something called impulse. And then we'll see, I'll just introduce the concept, and then we'll see where it comes in naturally out of Newton's laws. So impulse, I'll use the letter I. And it's actually a vector. It's a force exerted over a certain amount of time. So the units would be newtons times seconds, for whatever it's worth. We're going to hold off on the units because they're going to have a different form in a minute. But we know, right? Newtons times seconds. And you can see this is already kind of a collision phenomenon, because if something collides, there's a force involved, and there's a time, and often it's a short time for the impulse, so we'll just call it delta t. So this is the impulse, and the way we can bring Newton's laws into this is to immediately consider an interaction between two objects. So that would be a collision, like we were just looking at. When I have collisions, I draw a tennis ball, and we have force of 1 on 2 is equal force of 2 on 1 with a minus sign. That's Newton's third law. So when we're talking about collisions, we're going to bring together the fact that they're equal and opposite forces, and that they occur for a certain amount of time. There's a little duration during which the collision occurs. Okay. So that's what we're thinking about. This already is a collision. And now I'm going to define momentum. These are the 3 ingredients that we're going to use in this section here. So define momentum. It gets the letter P, and it's just the mass times velocity. Momentum P, mass times velocity. The units are kilograms times meters per second. They don't get a new name. It's just the units, kilograms, meters per second. Good. And I'll put a note here. If you're talking about purely kinematics, then you'd say V is just a kinematic quantity. Right, we had our kinematic equations, you know, we have accelerations, velocities, positions, and so forth. So the velocity in here was purely a kinematic equation, but if you put some mass behind it, momentum, so P equals mv, is a dynamic quantity, okay? Just to have some terminology here. It's dynamic versus just kinematic. And dynamics then refers to forces. Okay, so kinematics versus dynamics. And what's the difference? Well, if this were, just happen to have this in front of me, if this were just a chunk of styrofoam and I tossed it to you, you wouldn't be worried, right? But if I toss this brick at you, then maybe you want to wear gloves before you catch it or something. It could have the same kinematics, a piece of foam across the room that has the same kinematics, but this one of course has a lot of mass behind it. So that's the difference between just motion and when you're talking about momentum, you've got some mass behind it. Now, I can put these ingredients together . These ingredients together. I've got the impulse, I've got Newton's third law, and I've got momentum. So next, we're going to look at impulse equals F delta T. I'm just going to keep going. What do we know about the force? The force is mass times acceleration times delta T, and it's mass times change of velocity divided, you know, per time times delta T. And you'll see the impulse, I can cancel these delta T's. So this is m delta v. But mv is momentum, so we can say impulse equals the change of momentum. Impulse equals ... change of momentum. Remember, we had change of velocity with acceleration, but impulse now is the dynamical quantity, just as momentum is the dynamical quantity. So that's something we've now learned by putting these things together here. And we'll do some impulse calculations on the homework. In fact, on the homework, we will do some very simple momentum examples just to get a feel for the concept, and we can also do some impulse calculations. I'm going to end with, this is going to be a shorter lecture, I'm going to end with the evaluation of this point 2 here. So now consider the collision, and we have plenty of room here, so we'll write out F12 equals minus F21. Okay. And we'll say that this is the force of object 1 on object 2, and this is force of object 2 on object 1. So the next step in this equation, right, this is just description here, is we multiply both of them by delta t. It's certainly still an equation if I multiply both sides by the same delta t, but now you see this is a change of momentum. At this point I already have a change of momentum. That's what I just defined up there. Impulses change of momentum at F delta t. So let's go ahead and write out what we have directly underneath here. So we have the force of 1 on 2 delta t. So that is the change of momentum delta p of object 2, right? Because it was force of 1 on 2. Change of momentum of object 2 equals minus the change of momentum of our object 1, which means that let's write it out. Now we have change of momentum. We have M2 V2 final minus M2 V2 initial, so F and I final and initial equals minus M1 V1 final minus M1 V1 initial. So final and initial. I'm going to change that in a bit, but right now we'll start with that. So what we can do now is bring the 1's to one side and the 2's to another. And I'm going to put the 1's, or the initial, I'm sorry, we're going to put the initial on one side and the final on the other. And I'm going to switch the order here. And I'm going to end up with, make sure you guys do this by the way, M1 V1 plus M2 V2 equals M1 V1 prime plus M2 V2 prime. Okay, I've done two things at once, but I can explain it. What I'm going to do is let the unprimed velocities be initial and the primed ones be final, because it makes it easier when we're writing these things, because we're going to be doing a lot of this equation. So here unprimed equals initial prime equals final. Right? Unprime is this one, prime, that's what we call that. Prime. Okay, this calculation, very basic, right? We just took Newton's third law, multiplied, and everything else is just an interpretation. So really, it was this equation alone, a couple lines. But what we have here is called the law of conservation of momentum. We have a new conservation law, because this is called the total linear momentum. If we had 3 particles in a collision, we'd have all 3 of these. But here we're doing 2. By the way, I'm going to put vectors on here. We started with vectors. In fact, let's put vectors on all of these. So this is the law of conservation of momentum. And I have to note something also. There's an assumption in here that I didn't make explicitly. It's in this equation here. These are the only 2 forces involved, okay? So these are the collision forces. We have no external force involved, okay? We were talking about a collision, what 1 does to 2 equal and opposite what 2 does to 1. So these are what are called, the collision forces are internal forces. So important note here, internal forces and net external force equals 0. Force equals 0. So 1, 2. Net external force equals 0. So yeah, this law right here, this is what was before the collision, this is what was after the collision. The demonstrations I gave you already had all of these things, all of these features, and we'll work them out bit by bit. So what were the internal forces before we move on? There we go. So the internal forces were these magnetic forces of the cars acting on each other. Okay? Internal force. You know, I'm going to make a nice drawing of this. Because this will refer to our demonstration. Let's go ahead and, yeah, there's the conservation law. These are velocities. I'll do a sketch for this, and then everything I've written here will be explained and illustrated. So we'll just refer to the demonstration. We had these 2 cars on the track, okay? One and 2. And we did see them collide, and we did see them not touch. Okay. So that collision, where they don't touch, is due to an internal force because they have those magnets inside of them. So the internal force, those were the internal force magnets. The external force was mg, m1g, and n. Okay, these are the external forces. Now, the net external force is what was 0, right? N and mg balance cancel each other out exactly, so that the net external force is 0, and these things are moving without friction. These were the internal forces. Here, I'll give them a color as well. These were our internal forces, and these blue ones are our external forces. So when the internal forces let's remove the and here. We have internal forces, period. Those are the ones, you know, the forces that are involved. And the external forces, the net external forces are 0. I don't want to imply that the internal forces are 0. Okay, those are the, no, they're not, but the net external force is 0. You could actually say that the net internal forces are 0, but that's for both bodies, so let's not go there for the moment. Okay. Net external force on an arbitrary body is 0. So there you have it. That's the law of conservation of momentum, and we're going to learn to use this in the similar way that we use energy. You know, we've got A and B, and we write the equation down, and then we just solve it. So I'm going to leave it right there for today. Let's see how we did. This wasn't short as I thought it would be. Very good. Let's put a homework up on the board. just to make sure we don't get out of practice. What do we have here? I had found a couple, so this is homework for lecture 17, chapter 6. I have 3 and 6. Let's see if we can't add something to the mix. Yeah, this is a chapter with a lot of great material. 3 and 6 are just a little bit about the definition. But now we have impulse 2. I'm going to put an impulse here. So yeah, we're just going to say 4 and we'll do 14 as well. These are basic impulse problems. Now, before we leave the topic, before we finish the lecture, I just want to remind you, always write things out as formulas. The book gives you numbers. When we start doing our quizzes, pretty soon actually, we're also going to have numbers, but the technique is to solve the problem, to set it up and solve it as a formula first, and then plug your numbers in. Good, and having said that, we will see you next time.